Hello, everyone. Good morning. Welcome to the 7th PYCHeM, the second day of the 7th PYCHeM. So we will start right away with the scientific program. I will pass the word to Professor Veronica de Zebermuch, that will be the chair of this session. See you soon and enjoy the Congress. Professor?
Yes, good morning. My video is blocked. Well, I will... Okay, good morning, everyone. It is a great pleasure for me to be the chair of this morning session devoted to material science. And moreover, it's a great pleasure for me to introduce two colleagues of mine who I admire a lot. So the first one is Professor Paulo Ferreira, who is going to deliver a plenary lecture, as you know. I'll briefly present his CV. Paulo Ferreira is currently full professor at the Mechanical Engineering Department of the Instituto Superior Técnico of the University of Lisbon, and he's also director of the Center for Advanced Electronic Microscopy, Image and Spectroscopy at the International Iberian Nanotechnology Laboratory in Braga, Portugal. He's also visiting professor in the Material Science and Engineering program at the University of Texas at Houston, United States of America. Paulo Ferreira has a PhD in Material Science and Engineering from the University of Illinois, United States, and a postdoctorate at the Massachusetts Institute of Technology in Material Science and Engineering. His main interests are nanomaterials, nanotechnology, electron microscopy applied to alternative energies, and bidimensional materials. Paulo Ferreira is Vice President of the Portuguese Society for Microscopy. He has also been a special advisor to the Portuguese Minister of Economy and Innovation on the government strategy for science and technology. He also belongs to the selection nomination committee of the Japan Prize, which is awarded annually to scientists and engineers from around the world who have made significant contributions to the advancements of science and technology. So it is a great pleasure for me to introduce my colleague Paulo Ferreira, and he's going to present a talk entitled Nanotechnology, Witnessing the New Industrial Revolution. Paulo?
Yes, thank you very much. Let me start by sharing the screen. Let me see here. I guess, can you see the presentation now?
Yes, perfectly.
I guess just one slide, right?
One slide.
Okay. So first of all, let me thank the organizers for inviting me. It's a great pleasure, and my special greetings to Professor Veronica, who I've known for a long time, and it's been great to work with her and for her leadership in this area. So today I'm going to mostly talk. It's going to be a more general talk about nanotechnology and this industrial revolution that we are experiencing. And then I will have a few slides about my research, specific research, but this is going to be a more motivational talk and just give you a broad view of the things that's going on. So let me start with a quote by Henry David Thoreau, which said, "It's not what you look at that matters, is what you see." And this question of what you can and cannot see has been in our minds for a very long time. And this is basically because it's related with the world that we live in and also the scales that we experience in our planet here. And just give you this notion of scales, I would like to invite you to travel with me through space at speed of light, 300,000 kilometers per second. We start very far away from our planet, and as you travel through space, you see a lot of things from planets, from galaxies, from comets. There is really a bunch of things that you normally don't see when you just look at the night sky. But it's very difficult for us to really appreciate these scales because we are actually not deal with these scales on a normally basis, and only when we get quite close to our planet that we really start understanding what these scales are about. So when we get into the sun, where the light takes about 8 minutes to travel to Earth, and then of course now close to Earth in the moon, that takes about 1 light second, and then of course in the planet with about 12,000 kilometers across, we understand this kind of scales. But what I would like to talk today is about a completely different scale, the scale that we actually cannot see. And if you zoom in, for example, into the city of Venice and look at one of the squares, you can actually see a droplet of water, which is, and then we can look in and see there is actually a bacteria. We can zoom into the bacteria, and we see there are actually, is composed by DNA strands. And if we zoom in into the DNA molecule, of course, we see the atomic scale. And even though if you are at the atomic scale, if we look in, you see the electron cloud, of course, and at the center of this atom, you see the nucleus, the protons and neutrons vibrating in space. And we can still zoom in and look at the quarks. So this gives a completely different perspective of the scales that we are talking about. And this is actually the scale that I'm going to concentrate. Even though early on, in terms of scientific endeavor, we were actually looking towards the outside, not the inside. So we're looking to the large scales, and actually the first instrument which was beneficial towards that was the telescope by Galileo, and in the 1600s. Of course, many years later, we have now another telescope, is now the Hubble telescope, which is floating in space, and of course now we get a much better understanding of the universe. And here is actually an image of the Hubble telescope. It's called the Pillars of Creation. This is actually nebula where the stars are formed. So here we are talking about from one side to the other about 4,000 light years. But this is actually interesting to understand nanotechnology, because it's within, as I said, within these pillars of creation that the stars are formed. And in fact, they play a role in the making of the chemical elements. Besides a couple of elements that exist since the Big Bang, most of the elements that you see in the periodic table, they're actually formed during this explosion of stars called supernova. And they basically produce most of the chemical elements that you deal with on a daily basis. And you can actually see here in this table, so the ones in red, you see here, the hydrogen was produced during the Big Bang, but you can see that all these orange are actually created during the explosion of these stars. So in fact, you see that many of them, most of the suns, they burn elements up to iron, and then after that you get usually everything else is produced by stars mostly. So it's actually not surprising with this fact that if you look at your own body, we will have the same elements that will be existing anywhere in the universe, because it doesn't really matter. The stars are everywhere. Of course, you can have different materials done by different elements, but at the end, the ingredients are always the same. So if you look at your body, you will see you can stack some, fill a tank of hydrogen, oxygen, nitrogen. You can stack some calcium, phosphorus, and sulfur, and then you see that you get most of the elements of the periodic table. Some they are poisonous, even. Some are radioactive, but we have about, as shown here, 10 to the 27 atoms of all kinds. So this is actually interesting, even from a philosophical point of view, because there is this idea, in the end, we are made from the materials done by stars. So this brings us to the question in terms of scale, how small are these ingredients, as I just talked about. And of course, just to give you a perspective, here's a a droplet of water, which is usually just 1 millimeter or so. And then because of this surface tension here, you get coalescence, so water gets absorbed, and you see smaller and smaller droplets. There is a point, of course, you can't see anymore. And this very small droplet that you saw here, if you look at the scale, that's about here, about 80,000 nanometers. That's so a little bit more, so about 10,000, 80,000. That's more or less what you can see with your own eye. So this is kind of the micron range that we can actually achieve with our, let's say, our optical system. And then we have, of course, the macro scale that we'll deal with on a regular basis. But then we have the other scale, which is the nanoscale, of course, that things we cannot see with your eyes, and we need actually quite sophisticated instrumentation that I will show later. So that brings us to the nano world. And here I would like to bring this talk by Feynman in 1959 in Caltech. And he was quite provocative. In general, he was, let's say, a very funny but also provocative scientist. He won the Nobel Prize in physics. But in that particular talk, he posed this question, which is this: why can't we write the entire 24 volumes of the encyclopedia on the head of the pin? And you're talking about 1959. So it was very provocative. Imagine 24 volumes written on the head of a pin. So this actually, if you look at do a few calculations. So if you have a head of a pin, which is 1.5 millimeters across, if you multiply this by 25,000 times, you get more or less all the pages of the Encyclopedia Britannica. So we can now do reverse engineering. We take the diameter of a dot in the encyclopedia, that's about 0.2 millimeters. You divide by the 25,000 times, and you get about 8 nanometers. So this is, in terms of atomic scale, that means about 32 atoms side by side. So this is this exercise basically tells us that if I can write the dot of a period of the encyclopedia with 32 atoms, I can actually insert the 24 volumes of the encyclopedia on the head of the pin. And of course, nowadays, we can do actually better. And here is an example of atomic writing with a scanning probe. You see here the word Star Trek. In this particular case, every white dot you see there is a single atom. So we can actually now write at the atomic scale. So that's actually that question about the 24 volumes posed in 1959. That's now not a problem at all. We can do even better. So that brings us into the nano age that we are in, which raises the following question. So what if we could assemble these base ingredients of life, the way the ones I show you, that means like this atomic species, the way the nature does it, which is atom by atom. So that's how nature builds large structures, even macrostructures, is by building these basic ingredients of life one by one. And so that brings us into the so-called bottom-up nanofabrication or self-assembly, where you basically following these laws of nature. So here's an example of a molecule that has, a pink side and a green side. They don't like each other. You put these molecules in solution, and of course, you don't need to have any kind of human intervention. And of course, just by trying to minimize the energy, the green side of the molecules will actually align to each other, and the pink, because they don't like the green, they will separate. So the end result of that is basically you create this bilayer here. We have this in our bodies, lipids But you see here the nature at work without even human intervention, just simply just self-assembly, which is the way nature actually works. Another example is, of course, the carbon nanotubes. If you are under certain conditions of pressure and temperature, these carbon atoms actually fold into these tubes, which then, of course, materials with very interesting properties. But again, you don't need any kind of intervention. It's basically like self-assembly into these kind of structures, provided you get the right temperature and pressure, and that you can do that. And here's actually an image from the scanning electron microscope. You're looking edge on into the length of one of these tubes. You can see the opening, and they are in fact quite real. So then, of course, the idea is just you can start playing with these kind of structures. So what you see here is actually is two carbon nanotubes, and then you see this blue and green. They are actually they are ligands, where you can attach these to the carbon nanotubes, and then you can see that you can form these gears. And is it interesting to point out here is the speed or the frequency here. He's talking they are 70 gigahertz. So if you think about, for example, when you're driving a car that goes at about 2,000 or 3,000 rotations per minute, we are talking here about 70 billion times per second. So this is a huge rotation speeds, and you can see here the time. This is in picoseconds. So of course, this is, enables technologies are completely different here. So, and then with that, of course, the idea is to build machines. And in this case, these machines, for example, here you see you are inside the blood vein where the red blood cells going around, and then you have these machines that you throw them by the thousands inside your body. This one, for example, here to pick up cholesterol, and they will be, of course, controlled by computers. So this brings a lot of ethical issues. But now you have these nanobots and machines that can actually enter the body and do the work. So in the future, you are not going to the doctor. You actually swallow the doctor. The doctor will be inside your body actually doing the repairs instead of having some external intervention where you go from the outside to the inside. So it works from the inside out. And this is going to be a trend. So now it would be interesting to ask how is nanotechnology shaping the world? And you have to think about, there are three main things. One is in the digital world. And in this case, you have to think about this Internet of Things that you probably have heard. This Internet of Things, what you have is basically just everything you can think of is actually connected to the net, and so these objects will start interacting with each other. And so, just to give you an idea about what happens in 1 minute internet, this is data from 2019, and this is really absolutely amazing. For example, in Facebook, 1 million people logging in. Then you have here, for example, Netflix, about 700,000 hours watched in 1 minute. For example, if you think about emails, about 188 million emails sent. So this means that the objects now become subjects, and this is this digitalization of the economy is going to play a very important role. Now, having said that, of course, you have to understand that this is only possible by the existence of materials. In this case now, using photolithography, you have this top-down nanofabrication. So you have these wafers of silicon, and then by light exposure through masks, you create these kind of circuits. These circuits now are three-dimensional circuits, quite complex. And this is basically most of the electronic components are done in this way. Now you have to understand that now the first transistor at about 2 centimeters. Now, if you look at these scales, this you can see here a needle. Now in a square centimeter or so, you have there 20 or 30 billion transistors. So the scales are incredibly small. We're talking about things below 10 nanometers now for these kind of devices. So now you really have a huge amount of these devices in a chip. So this has been a remarkable growth, and then so you have. I think it's important to understand that this digitalization of the economy, sensors and internet and everything is only possible because there is this development materials. In the end, you need materials to actually do the computation and just develop this area. Of course, in the future, the idea is maybe which is now silicon. This is going to be mainly carbon. If you look at the periodic table, the carbon is just on top of silicon. It's similar properties. The silicon is a semiconductor. The carbon can have also properties of a semiconductor as well. I mean, our brain is mostly based on carbon. The computers are mostly based on silicon, but they actually a lot of similarities between these two elements. And of course, there is work now on using carbon for the new computers. In fact, I will show you later about the new computers, the quantum computers, that is already one at IBM. The second aspect, which is shaped by nanotechnology, is actually the bio area. And here there is, for example, the bio tattoos. These are kind of similar tattoos you put on the skin. But you can see here, this is actually the tattoo has a lot of devices and sensors. So, for example, in this case, they can be monitoring in real time many of the parameters of your body, like blood pressure and other aspects of heart rates and things like that. So this is a way of monitoring your health. And this is going for sure. This is what's going to happen in the future. So instead of going to the doctor when you are feeling sick, it's going to be more on the prevention side. So at all times what's going on. So a slight change will trigger some alert, and then you can prevent things from happening. And so what you expect is, of course, in the near future, you will have a lot of sensors across your body, in the brain, in the heart, in the spine, and this will be connected through the internet, maybe to your doctor, maybe somewhere else. So you can actually be monitoring in real time your body, and then allows you to keep it in good shape and prevent anything from happening. The other area which is being impacted by nanotechnology is on drug delivery. In this case, you have, for example, particles is one example, nanoparticles that can be delivered through your body. They will, for example, in the case was shown here, you have a tumor, and then these particles can actually recognize the tumor, and they can basically attach, and then by means, for example, thermal means and so on, they can kill locally the bad cells. So in other words, instead of having these chemotherapies, another therapies which are tend to be harmful to a certain extent. Here, you will be locally attacking the illness in some way. Even more amazing is this bioprinting. This is actually from 2017, but you can see here is printing of muscle tissue. That's also real cells here. You see that it's still slow. You can see the time running, but this is actually is amazing, amazing achievement where you can now print out, let's say, human tissue or some sort of a copy of human tissue. Very simple, of course, but still amazing. You can do this in printing, like you are printing paper in a laser printer, and now you're printing human tissue. And here is actually the reaction. So this is actually muscle. So you can see here that the muscle actually contracts, and pretty much like the muscle would behave in this situation. So this is things that sometimes difficult to really understand, but this is how we're going. And of course, it's possible now with scaffolds and things like that to start doing things like ears and parts of body that are possible with the new technology. And the last aspect is the fact that the fact that you have new materials. This is of course a big area where, I mean, the scales allows this possibility of creating new materials that are going to be quite interesting. So one, for example, is the 2D materials. This is, for example, here's the case of graphene. This will be very useful for quantum computers. So in that case, you can modify these. These are single-layer materials. For example, graphene is one example. You can have also metal decalcogenides like molybdenum disulfide or molybdenum diselenide or tungsten diselenide. They are another examples. But what you try here is either you dope, so you substitute, for example, in this case of graphene, the carbon atoms by dopants, and then another strategy is to create vacancies. So in that way, you remove these carbon atoms. They are removed very precisely, and you get then some quantum states there because of these vacancies of dopants, and it allows you to do, for example, single photon excitation and things like that. So allows for some the quantum computers to actually be built. And there is already actually one. This is IBM Q. This is maybe looks something like from science fiction, but this is actually a computer, a quantum computer, which is sitting in IBM Zurich. And this is already performing. It's amazing performance. There's still a lot of issues, of course, with these quantum computers. But the advantage of those is because you have this kind of double state, so kind of this Schrödinger's cat example. So typically, if you have, let's say, in a typical computer, you have the binary concept of information. So you're like the 0, the 1. That's what the transistor normally does in a normal computer. Here, you can have the 0 and the 1, but they can have actually both occurring at the same time. And so this actually has huge ramifications in terms of computation capability. And one of them is that you cannot interfere with this information. So if you are passing information across, let's say, a cable where you are transmitting, let's say, an email, and if I interfere, I will break that kind of the 0-1 the simultaneous state, so it goes back to 0 to 1. So I cannot actually interfere. This is good. You can only send information and only receive it. Any kind of intervention in the middle, you will actually will break, and so this is very good for encrypted messages and kind of a safety. But there are of course other ones, mainly very high speeds. So there was one example that you could do in what you could do in 200,000 years would take just a few hours in a quantum computer. The other one interesting is the field of metamaterials. These are materials that actually create this kind of invisibility. So here's an example. You can see that the person actually putting the hand, but you don't see it. This is the way it works. You get the deflection of light. So this is nothing that the laws of physics just go against. Is basically a deflection, but as a result, you get this invisibility. And of course, there is some people working on that. This is quite a big field, this metamaterials. And that's kind of a funny thing. Then maybe you can do what Harry Potter can do here, and then you might go around with an invisible clock, and you can actually, I don't know, you can just go to the street and make sure nobody can see you. But this is, of course, the future. But right now, it's a large area of research. So what is actually new in this fourth industrial revolution? And I think this is important to understand. That we had, of course, the first three industrial revolutions. But I think what is now, people talk a lot about digitalization. But what is actually happening for the first time is the fact that you have these three worlds that normally were disconnected. The digital world that I was just talking about, like say the bits, the bio world, which are the genes, and then you have the materials like the atomic scale, and they were not able to communicate with each other. But in fact, they are able to communicate at these very small scales that I was talking about, so the nanoscale. And so this is what actually makes possible now all this interaction. So I make a material that can interact with the let's say, my body. At the same time, I have some device that I can connect to the net. And then all these are now connected because in the end, these worlds, they communicate at this nanoscale. So this is what allows the nano technologies, in fact, the glue that allows these three worlds to communicate. And this is now bringing is revolutionizing this kind of science and technology in this area. Let me just say a few things that have been some applications that have as a result of that. One, for example, is nanomodified coatings. Here's an example of a leaf of a plant, and of course, these leaves are hydrophobic. You see here the water coming in, and then it doesn't wet the surface. So if you look in more detail why this is happening, is because actually you look at the nanoscale and you see the leaf as this kind of features, and that is actually preventing the water from the water droplets from wetting the surface. So this is with that in mind. Of course, people have been doing similar things. Here is an example of a surface following this kind of example, and where you can now get hydrophobic surfaces pretty much following this idea of the leaf. Another example is this kind of surfaces where you have both photocatalytic action. So in this case, for example, TiO2 on the surface of could be let's say a wall of a building. You get upon reaction with light, UV in this particular case from the sun, you get the production of radical groups, and these are great in terms of destroying cells and with the production of water, CO2. But this is actually now being used in some of the surfaces, hospitals and buildings as an example. Here's an example of the church in Rome, where they have this kind of coatings, and then these are basically self-cleaning in some way. There is also some of these applications in hospitals, particularly with antibacterial surfaces. Again, back to the devices. So you expect the cities of the future to be along these lines here. You will have all kinds of sensors. So from temperature, humidity, acoustic, chemical, electric, magnetic acceleration. So basically the city pretty much is going to be all connected, many sensors. So you are monitoring basically all aspects of city life. And then this will allow what we call this Internet of Things, but will allow a completely change of the way we live and work and so on. So that's kind of related with the digitalization of the economy. But as I mentioned before, this is because we have this kind of materials in some way that allow these sensors to be fabricated. Another interesting area is in this kind of biomimetic materials. This is, for example, the case of a gecko. This is a lizard, which, if you look at the toes of these animals, you can see that they are actually built by this kind of very fine pillars, kind of the nanoscale. And this is just basically van der Waals kind of bonding, because you have so many surfaces, then they can sustain their weight on the on a surface, even just on a single toe. And with that, what people are doing is, of course, this is an example of the mechanism. So basically, what happens with the gecko is as they move around, you see that. You have a lot of contact, surface contact, and then basically this allows the gecko to sustain his weight. With that in mind, some robots have been built, developed. In this case for buildings. So, for example, this for cleaning, and other. You see here some of these robots. Actually based on the gecko. Here is one for fire, another one for surveillance. So this is actually interesting that we take this biomimetism and then create some of these interesting aspects in terms of applications. Another interesting one is the abalone. If you go to a French hospital, French restaurant, you will actually, this is kind of a delicacy, and this is similar like to a mussel or clam, but you have this experience that is not easy to break. The reason is that if you look again at the very small structures, you have this ceramic, this is calcium carbonate. Basically, you have these layers, as you see here in this image. But what you don't see very well is between the layers, there is a very nanoscale layer of polymer. So in fact, if you try to break it, the fracture propagates relatively quickly through the ceramic material, but then encounters this polymer in between the ceramic layers. And of course, it gets deflected. So it's not very easy to propagate the fracture across all these plates, because of this intercalation of polymers in between. So this is a very interesting structure that actually gives this kind of strength that is that you experience when you are actually dealing with these things. And just one last example of a space factory. So this is an idea going to Mars, trying to build homes, and then what is basically you take the material that is in the surface, and then with you actually build homes from scratch from the material that you have there. You just need to bring the machines there, and this is of course have other applications, like in the case of catastrophic events like floods or even political events like refugees and so on, where you can build these homes very quickly by 3D printing. Let me spend just a few minutes talking a bit of some of the things I do in my group. I use mainly advanced electron microscopy. This is kind of the research lines in my group. Some work on battery materials, also on proton exchange membrane fuel cells, 2D materials I just talked about, and then something is called flash sintering. The way we approach this is we are, if you look inside, we are trying to understand the relationship between the structure of materials and properties, and through the characterization. So we use advanced electron microscopy, electron spectroscopy, and then we do image simulations and data processing to basically understand this relationship between the structure and the properties. And here's the areas on the left. I'm just going to give a couple of examples. So here's one for the case of the battery materials. For those of you who have not thought about how a battery works, you have an anode and a cathode and an electrolyte. So in this case, for example, when you are discharging, you see here the lithium in red going from the negative to the positive side. And then to compensate for the charges, the electrons will actually go through the outer circuit. And then, of course, you have the reverse process. And when you plug, let's say, your computer or your cell phone into the wall, so you start charging, you get the reverse process. You get this lithium now moving from the plus to the minus, and then the electric charges, of course, going through the outer circuit. So you basically have this kind of shuttle between back and forth as you charge and discharge. For the cathode side, these are lithium based. You probably have heard. There are a lot of materials out there, but of course, what you want, you have high potentials and high capacity. So you like to be on the upper right. This is, of course, not easy, and there is a lot of materials here with about 4 to 5 volts, and then about, let's say, 150 milliamps hour per gram. And for example, just to give you an idea in terms of an approach, here's one material which is widely used, the lithium manganese 04. So what we do, for example, is looking at the atomic structure. So first we basically look into the atomic model. So we build these models, really understand the position and of these and the orientation of these structures. So for example, here, the lithium in green, the manganese in purple, and the oxygen in red. And we would like to orient this in a way as, for example, this one, where the atoms are on top of each other. When we do that, this is a computer simulation of the structure. Just look through that direction, and you see this diamond. This is actually, with this technique, what you see is the manganese atoms. You cannot see the lithium and the oxygen, but you can see that the manganese forms these diamonds here. So then we can actually go to the microscope, and as shown here, this is a real image from the microscope, and as you expect, inside is exactly this diamond where you see the manganese atoms. But you see that on the surface is actually rather different. You see that in between, in the middle of the diamonds, you have actually 2 atomic positions actually filled. That means that the structure has been changed at the surface. So this is actually an example of using the atomic structure to understand that something has changed. And when we use eels, that's another technique, it's a spectroscopy technique in the microscope. What we realized was that in the bulk, the manganese had valence states between 3+ and 4+, but then on the surface, the manganese had 2+ and 3+ valence states. So actually, we know now that these atomic positions were filled with manganese and with a valence state of 2+. And this is, we can get this right now at the atomic scale. Another area of interest is the proton exchange membrane fuel cells that I'm interested in. This is, again, a new, is relatively, let's say, is going to be important for the future. You have hydrogen coming in from one side. You split the hydrogen in two atomic species. You take the protons across the membrane. The electrons will go out outside the circle. On the cathode, you insert oxygen. And then, so when the electrons reach the cathode, they will actually merge with the oxygen atoms. And then the protons coming from the other side, you get water vapor. So this is a very clean technology, hydrogen in, water out. And then at the heart of these fuel cells are catalysts that are sitting on the anode and the cathode. If you actually look in detail, this is actually, before you cycle this fuel cell, you see the particles here in dark. They are very small. You see here the particle size distribution, about 2 nanometers. The rest is it's kind of carbon is a support where you see the particles sitting on the carbon. The problem is just when you start cycling this, you get a huge increase in the particle size. So remember, it was about 2 nanometers. Now it's about 8. And you see here from these images, the particles have grown a lot. And of course, there is a lot of work trying to understand why the particles actually grow in size as you cycle the material. And what we do, we do a technique that you can see this in before and after the same location. So, for example, you see here that before the particles were separated, and then after the 1,000 cycles, you see that they merge. In fact, there was this coalescence, and you can see here that on the left was polycrystalline material, and on the right is a single crystal. More interesting also is the carbon that it was, you see on the left, the planes are actually very well aligned, but on the right, they get deteriorated. You can see that better here. The carbon has got destroyed, went through carbon corrosion. And this is typical of the case where when you have an hexagon structure or the carbon, and when you start to get carbon vacancies, when you move from hexagon to pentagons and heptagons, you start to get this wavy kind of reaction because you get this bond angle. And therefore, this is a result of the fact that you have carbon corrosion going on. And this allows us to actually look at this in real time in the microscope. So, for example, you see here particles, very small, the nanoparticles, and you can see then they in real time. You see here that as the carbon gets corroded, if you see here on the left of this particle, you see the particle then starts moving. And this is kind of the mechanism for motion. As carbon corrosion takes place, the particles will start to move. So you can see these things get a huge insight into what's going on here. More recently, we have been now tomography. So actually you get a much better feeling, a 3D perspective of these particles within the carbon. So it's you get a much better understanding how these things behave and where the particles are, and they are misleading many times if you look just at 2D projections. And here's an example of, again, we do these reconstructions at 3D, so then we can just rotate and fully understand what these things are. Just to finish up, another example about flash sintering. So the idea is to sinter ceramic materials. This is basically through densification and coarsening. And the local driving force is this kinetic. So in other words, the curvature, you have positive curvature and negative curvature. And so there is a difference in chemical potential between the top and the bottom. And so this leads to a flux of atoms where the atoms move from the top to down and the vacancies from the valley to the top. The interesting thing about flash sintering is just in addition to temperature, you apply electric field. So now you have an extra flux due to the field. The advantage of this, you can sinter materials. You can see here on the right, you can lower the temperature very significantly, almost like 3 times lower just by applying the field. And here's, so in other words, the conventional sintering, so for example, you use 1400 degrees Celsius, but now you go with flash sintering, you go to about 800, and you see that instead of hours, you take about seconds. And so you can take these particles and sinter them with a field very quickly under low temperatures. So here's some things we have been doing where we are trying to understand this at the atomic level. This is with zinc oxide, and then try to see how they sinter. This actually first experiment was extremely fast, and then they emit light during the process. And then here on the right is with TiO2 nanotubes. And you can see that as you apply temperature and field, you see here's a polycrystalline structure here. But then as you get this going, you move this, you get basically to a single crystal, and you even go to the melting state. So this is the field actually brings a lot of, still not well understood the mechanisms, but this material that was polycrystalline now is becoming almost like a single crystal, basically because of this sintering process. Just for the sake of time, let me just move on into the future. Just a couple of things. One, I would like to, for students, this is important. We tend to develop at universities cognitive intelligence, but I would like to leave a message that emotional intelligence and contextual intelligence is going to be very important. The emotional intelligence, things like motivation, empathy, social skills, self-regulation is going to be very important. And then this contextual intelligence is that you're going to be, you have to be more transversal, deal with the people from the government, from the business, from the civil society. So you cannot be in silos. You have to have much more this kind of contextual intelligence. A couple of things by 2025 that people are predicting. So 10% of people wearing clothes connected to the internet. This is almost 90% chance. And you have many things here which are interesting. Here, maybe the last one I find very interesting. You have the first artificial intelligence machine on a corporate board of directors. This is about 45% of probability that it can still happen. And then I should mention also that what happens to professions, a lot of professions are going to be substituted by robots. So that's going to happen for sure. And then I feel, of course, some ideas out there completely up in the sky, like the space elevator. Instead of having a shuttle or a rocket, you would just have elevator. The holodeck that you can see now in, of course, classes, but this could be very interesting. And of course, this is maybe more disturbing. I don't think this will happen in this way, but this is a discussion of cyborgs. I think it will be more sensors and things like that within our body. And then, of course, things like in defense, spies. These are is a fly that is basically a spy and take pictures and collect information. And I would just leave this. This is a movie. I will finish with that. What you see here, every single dot is an atom. And so this is a movie done with the single atoms. Okay, with that, I will be happy to answer any questions. Thank you very much.
Thank you very much, Paulo, for a truly amazing and inspiring talk. I haven't received any questions in the chat, but I do have lots of questions if you care to answer to one of these. You've talked about digitalization, circular economy, so forth. What about sustainability and nanomaterials? Can you give us your opinion on that?
Yeah, I think there will be a very important role. Again, I think this, I mean, in many aspects. I think one of the aspects will be, of course, with sensors, because a lot of the sustainability issues would have to do about, for example, monitoring air quality, monitoring soil quality, monitoring water quality, and things like that. So this, I believe, this is going to be. You will have sensors, they can monitor this in real time. That's going to be one aspect. The second will be, of course, in recycling. These nanomaterials, they will play a role, particularly this kind of porous materials that they have an important role in the recycling aspect. But I guess in many value chains, depending on the value chain you are talking about, I think they will be very important. Again, from the raw materials all the way to the recycling, I think you should think about those nanomaterials as playing a role there. But I would say these two, I think would be new materials, particularly these porous ones, and then the sensors. I think they are going to play a huge role.
Yeah, I agree. Another thing, you mentioned several times aerospace engineering, and I have always had this feeling that things in aerospace engineering are much more advanced than here on Earth, meaning that we go to Moon, we go to Mars, you use terribly advanced nanomaterials, very advanced techniques. And then you go to Earth and we don't use it. Which is the bottleneck? Price, processing? What do you think?
Right, definitely is the case. So I think, I mean, this is an interesting discussion because people sometimes think about these space programs as the objective is to go to Mars and of course, I mean, this is the objective, but people have to understand that there are a lot of spin-offs or spilling from those interactions, because when you're trying to bring someone to Mars or having this kind of space travel and so on, I mean, there is a lot of technology because it's extreme conditions of all kinds of radiation, energy and so on. So during that time, there is a lot of technologies that actually occur. And you have many examples there that spin-offs from that. Then, of course, based on what you said, is just, of course, when they go to space, they don't care much about the price. And so, for example, if you think about the fuel cell, the space shuttle program had already fuel cells in their shuttle. I don't know, this is maybe 10, 20 years, but it costs like 10,000 or 20,000, they don't care. Because then, of course, if you put this in a car, a fuel cell costing 10,000 and 20,000 just go for a trip, of course, this is not visible. So I think on Earth, there is always this issue that there is a lot of the technology already working, but then, of course, there's the economics, and of course, you have to have mass production, unless he's going to be for the, I don't know, one king or something somewhere, it doesn't really work. In the space, from the interactions I had, they basically don't have the constraints. The constraints they have normally is weight, and of course they think about the money, but what they think is about weight, because it's about, I believe, if I'm not mistaken, is about 10,000 euros per kilogram. So everything you do there, if you put one more kilogram, it's about 10,000 more. And so they think about that, but in general, they in terms of technology, they don't care about the cost. cost of the technology. I think that's the reason. And so, but I think the important point is we always have to think that there is always these spills that is not okay. Just going to the moon. Why are we caring about going to the moon? But there is a lot of things that result from that.
Okay. Thank you very much again, Paulo, for a truly interesting and motivating talk. Thank you very much.
Okay, thank you very much. Bye-bye.
Okay, so it's now time to pass to our second lecturer. The speaker is now Nuno Silva, as I had said before. Nuno Silva is a physicist working essentially among the chemists and chemical engineers with a strong research profile in magnetic nanoparticles, in nanothermometers, and hypothermia. He received a degree in physics from the School of Sciences at the University of Porto in 1999, and he received his PhD in physics at the University of Aveiro in 2006. He then earned a Spanish Research Council grant to develop magnetic nanoparticles for biomedical applications at the University of Zaragoza in Spain. In May 2009, he joined CISECO in Aveiro, where he currently leads a group devoted to the development of magnetic nanoparticles applied essentially to nanosensing. He became internationally recognized in the field because he measured for the first time temperature at the surface of magnetic nanoparticles used as local heaters. He received an award for encouragement of research by the Materials Research Society of Japan in 2014. So it is my pleasure to introduce Nuno Silva, that I've known for many, many, many years. And his talk is entitled Development of 3D Temperature Thermograph at the Micro and Nano Scales. Nuno, please.
Thank you, Veronica. It's a great pleasure to be here. It's a great pleasure to have you as a share of this session. It's really nice to be part of this celebration to science, to this celebration to chemistry, and to this celebration to the future. We had just a great talk from Paulo, so I hope I can keep the pitch to talk to you about a little bit about the past and a bit about the future. So let me just try to share my presentation here. So, does it look okay now?
Yeah, perfect.
Okay, so thank you. Good morning to everyone. So this is our contribution from CISECO at the University of Aveiro. So good morning from Aveiro. So let me just go. This is the present. As Veronica said, so we are dealing with the problem of measuring temperature. So measuring temperature in small scale, so the nanoscale, the microscale that Professor Paulo has just introduced us, and to measure that without wires, so to have the image, not the image of the atoms, the image of temperature, the image of heat. So this is our motivation. This is we are devoting our scientific lives to this issue. We started by measuring temperature without wires at the distance in single points. Then we evolved to a line to measure temperature in one dimension. Then we got temperature maps as this one that I'm showing here. And from this point on is what I expect to be the future. So to go from this surface to actually a thermography, to actually a 3D model of temperature, and if possible in real time to understand processes involving heat. But why do we care about this? Because heat is being generated at the micro and at the nanoscale. So heat is being produced, for instance, here in MEMS, in these ships that Professor Paulo has just introduced us, heat is being produced. And when it happens in this case, it's basically a bad signal. It's signal that something is not right. It's signal that something is going to fail in near future. So you really have to take care about these hotspots. Sometimes it's opposite. For instance, here, this microfluidics. Sometimes you deliberately want to generate heat in a given spot, and you want to do that to make chemical reactions, for instance. So here's a microfluidic setup where you are making a chemical reaction, the denaturation of a protein, in fact, and you need to have controlled temperature to have the reaction that you want. And so you need to monitor temperature. And these heat processes are also happening in cells. So cells are basically heat machines and chemical machines. And so heat is being produced. And to answer the question of how much heat is being produced, where is it being produced, and where is it being flushed, you need these thermometers. And so is the kind of answers that people working in this field are trying to answer. So why 3D? Why do we need 3D temperature measurements? Well, the obvious answer would be we live in a three-dimensional world, but it's a bit more tricky than that. You can think about heat flow. It has a lot of similarities with the flow of current. And we know that the flow of current can happen in a wire. So basically, you have a high potential here, you have a copper wire, and current flows from the high potential to the lower potential. And this happens in one dimension. And if you have a sheet of copper, the current will flow in 2 dimensions. So why are we not satisfied about measuring heat in 1 or in 2 dimensions? Basically, because while electric current, we can find electric current in 1 dimension because we have very good electric conductors and we have very good electric isolators. So you have the electric current just inside, confined to the wire. But we don't have such things when it comes to heat. We don't have such good heat conductors and we don't have such bad heat conductors. So it's really difficult to confine the flow of heat in 1 dimension. It's really difficult to confine the heat of the flow of heat in 2 dimensions. So in practice, heat is always flowing in 3 dimensions. You cannot confine it. So in practical applications in real life, it's flowing in 3 dimensions. And so if you measure temperature in just 1 point, in just 1 dimension, you are just having a partial view of some reality which is intrinsically 3-dimensional reality. And so that's why people care about measuring temperature in 3 dimensions. And practical aspects, for instance, in this kind of treatments. So tumor ablation by heat. So you just, at the distance or inserting some laser device, for instance, you can eat up a given tumor. And of course, you want to know how deep you are eating. You want to know the volume that you are really targeting, because you need to target the correct amount of volume with the correct level of temperature. And so that's why people care about measuring temperature in 3 dimensions. And it's actually a relevant question. It's a growing market, this tumor ablation with heat. And if we go down in scale, so from the scale of a tissue to the scale of a cell, you also have these heat processes coming out from mitochondria, for instance. And if you want to understand these heat processes, you need to measure temperature. And if you measure temperature in the 3 space dimensions, you can understand where heat is being generated, and you can understand where it is going. So that's why people care about measurements at these length scales. And how do people do this? So when you think about things like PC boards, MEMS, you can think about complex So you just take the approach that it's being made at the micro scale. You just think about that same strategy and you make it smaller and smaller to adapt to the length scale of your structure. So these are, where is my pointer? Okay, here, these are basically thermocouples, so junction of two metal contacts, but made at the micro scale. So it's the same physical principle that you use at the macroscopic scale, but you just made it smaller. And our approach is here, and it takes advantage from the microscope techniques that Professor Paul was just introduced us. So if you think about the old thermometers, the old mercury thermometers, or fluid thermometers, where the temperature is related to the expansion of a fluid, you just think about making them smaller, making them nano. So you take a nanowire here, a nanotube, you fill it with a fluid, typically gallium, for instance, and you see how this fluid expands and contracts with the change of temperature. Some techniques are here, some between the contacts and the wireless techniques. And this is the case, for instance, of atomic force microscopy. So it's typically atomic force microscopy, but in this case, you put a tip with a well-known resistance, and by knowing and measuring the current, the electric current, and the potential across this resistance in the tip, you can understand temperature, and you can understand also heat flow in surface. And then on the other side, you got these wireless techniques, which are much more flexible. So it allows you a much more flexible configuration because you do this at distance. And this is, for instance, the case of infrared thermometer. So the same principle of the infrared thermometers that people use nowadays, for instance, in airports to check for the temperature of passengers. So imagine the same principle, but now coupled to an infrared microscopy. This is something that we have here in Aveiro. So you can have these thermal pictures, and again, I don't know here, you can have these thermal pictures of infrared radiation, but now with the length scale of micrometers. You can also do this with light, with the fluorescence of some objects, typically the fluorescence of some nano and molecular objects. So you typically excite these objects and you read out the light that they are emitting. And from properties of this light, you can understand what is the temperature of these objects. And you can do this with very high space resolution, and you can bring out maps of temperature. So in tissues, so the important application that I told you before, the application of measuring temperature at the distance during tumor ablation. So nowadays, this is something which is already in clinical practice. So this infrared laser coming and making an ablation of the tumor, nowadays it's still made with a single thermocouple. So a single thermocouple here close to the laser, trying to measure the temperature here and trying to get the right spot, trying typically to avoid this coagulative necrosis and try to get to this plateau here where temperature is kept below 50 degrees Celsius for a given period of time. So this is the present, but people are of course thinking about future, and future is measuring this in 3 dimensions. And what people are now trying to do is to use MRI. So the magnetic resonance imaging technique that you have virtually in every hospital, at least in developed countries. So try to use MRI to have an idea of what is temperature inside this tumor and around. to know exactly the dose that you need to give to the patient and the amount of energy and the amount of time. And so you can do this, for instance, using this PRF thermometry. PRF stands for proton resonance frequency. So the resonance frequency of the protons, which is the base of the MRI image process, this frequency has a small temperature dependence. It slightly changes with temperature around room temperature. And so if we are able to measure this frequency very precisely, we can have a measure of temperature. And then MRI technique, so this excellent technique, gives you the third dimension for free. So if you are able to get a technique that gives you temperature using MRI, the MRI gives you already the tomography by free, and it's a technique that is already implemented in many hospitals. So there are lots of people trying to solve this issue. Also, there is also another technique, that tomographic technique, that is expected to come into the market. It's called magnetic particle imaging, MPI. So if you Google for MPI and Bruker came out with this preclinical imager. So what's the point? The point is this new tomographical technique is much faster than MRI, much faster than the normal tomographic techniques that you have, MRI, PET, and all of them. And being much faster means that you can perform real-time experiments, real-time 3D measurements. And it's this video that Bruker has here. So it's basically a tomographic image of your heart. In fact, a heart of a mouse, for sure, of a mice. And it gives you in real time the flow of blood inside your heart. So by being much faster than MRI, so those who have made an MRI, you know that you typically are there something like 15 minutes to get an image. Here you can get that in real time, less than seconds, you can have this nice image. So if you can come up with a way of measuring temperature, exploring this technique, you get this 3D with time resolution image of temperature for free. And some people have already started this quest of developing materials to understand, to measure temperature, exploring MPI, so the magnetic particle imaging. They still suffer from a great problem, which is they cannot tell the difference between temperature and viscosity. So a change in viscosity, it's indistinguishable from a change in temperature. So that's why we still need a lot of research if we want to put this into the market, to put this into a reality. So we know how to measure temperature in tissues, at least how nature does it. When you think about a thermometer, you think about, so imagining this scale temperature, and here some other physical parameter. It can be light, it can be a voltage, it can be a current. So here is some physical parameter that in the y-axis is some physical parameter that you can measure. And here is temperature. And when you think about a thermometer, you think about something with a very well-known, predictable, reproducible dependence with temperature. So you want a variation that is as much as possible, as reproducible as possible, and without any change, without any hysteresis here. So just a linear curve going up and down with temperature. Let's see what nature does. When nature wants to measure temperature, nature is not concerned about having a real value about temperature. It's concerned about controlling temperature within well-defined ranges. So it's concerned about knowing if temperature is kept within very well-defined range. And it does this with a cell membrane protein like the one here. So this is a cell membrane protein. It's normally closed. And when temperature goes above a given threshold, it opens. And when it opens, you have a flow of ions across this membrane. And this flow of ions, eventually it gets into your brain. And so you have a warning signal. You have a warning signal typically at a given threshold that warns you that it's at a temperature above the one that you can stand. And this is the first warning. If you touch again a second time something which is hot, then the second, I don't know how here, the second warning comes before. And so this is a process called sensitization. So it's a nonlinear process. So the first trigger, it's here in the blue lines. The second trigger, it's a bit before. So it's a sort of sensitization. And then, of course, with time, these proteins forgot about the danger. And so if you get into a hot place again, it will get back to this first response here. So when it comes to temperature, nature has these different concepts: sensitization, memory about temperature, so that you don't make the same mistake again. So it's really interesting to think about this, and it's really interesting to think about how can we do this with materials, and how can we explore this with the materials. And so now the basic question of the present talk. So we love chemistry, we are involved with chemistry somehow. And so how can chemistry help to measure temperature at this scale? So some of the examples I just gave you are intrinsic properties. So this infrared emission is intrinsic from everybody's. So everything emits this infrared radiation depending on its temperature. Also this PRF, so the resonance of protons, it's also something intrinsic, but many times this is not enough. And so you need something that we can call thermometric agents. So if we're thinking about measuring temperature without wires, then you need something that you place there on the place where you want to measure temperature. And then this thermometric agent gives you information. Of course, information in the form of a wave, information in the form of a field, of an electric or a magnetic field, and you read this information from a distance, and you infer, you make a temperature map. This is the case here, for instance. This is carbon, these are nanodiamonds, and with these nanodiamonds, you can excite these nanodiamonds with green light, and you can collect the red light of these nanodiamonds, and the properties of this red light depends on temperature. And so you can have these nice temperature maps at cellular level. Where is my pointer again? I'm sorry. Here it is. So you have these nice temperature maps of temperature inside one single cell. Also here, the example I show you with magnetic particle imaging, these are basically magnetic nanoparticles. They give us an image of temperature and viscosity at the same time, but they are there. And by measuring their magnetic properties at a distance, we can have a map of temperature and viscosity. Also the case here of cells, these are molecules, these are fluorescent dyes that you can use. And also by measuring the fluorescent properties at a distance, you can make this nano temperature maps. So chemistry can really help a lot in developing, tuning, in producing these thermometric agents to enhance the information, to have better, well-defined information about temperature. So that was the quest of the group of Professor Carlos quite a decade ago, let's say. And so Back then, we start using lanthanides. So lanthanides have fluorescence. You excite them with UV light, and then you collect fluorescence. And by analyzing this fluorescence, you can have the idea of temperature at a distance. So back then we were doing this in a single point. So we were exciting with a laser fiber things inside the volume, and we were collecting the information with no space resolution. So we had no space resolution, but we had really high temperature resolution, because here in this red curve, you can see the typical curve that you get with a normal thermometer. And here in blue, you can have the temperature that we get from the nanothermometers, and you have much faster response, much accurate response to what is the temperature that you get there right on the top of the heaters. So typically these megamite nanoparticles, they play the role of the heaters. So it's like nano lamps heating up. And then you have the thermometers placed just around the heaters. And the temperature that you get from this local measurement, it's different from the temperature that you get from the average of this bulk solution. So we started with a zero-dimensional design, then we got into a one-dimensional design. So we were measuring temperature across this line in this electric circuit. So we were passing current through this electric circuit. So of course we were heating up, and we were measuring across this. And again, this is the comparison between this is the comparison between the black curve, which is the response from this nanothermometer, and this red curve, which is the response from the typical infrared thermometer that you have in airports, for instance. And you can see again a better space resolution of this thermometer, which is placed right on the spot where heat is being produced. So this is just another one-dimension example. So in this case, heat is being produced here. This is a fluid with these thermometers in suspension, and then you measure the heat flow. Our heat flows in this direction. Although, as I told you before, heat is basically spreading in 3 dimensions, but here we could get a measurement of what happens in this one space dimension. Then we got into a temperature map. So we just put these thermometers in an optical microscope. So in this optical microscope, we were looking at cells, and we were looking at the fluorescence of these lanthanides. And basically, we had 2 lanthanides, europium, which was giving a red emission, basically constant throughout temperature, and terbium, which was giving this green emission, which was changing with temperature. And based on this relative change, so basically the color, if you want, the color was changing from this yellow here to this red here. And so by measuring this color in an optical microscope, we were able to measure the temperature of a cell, and we were able to spot inhomogeneities. So inhomogeneities in temperature across the cell membrane here. So we got into the second dimension of measuring heat. So the synthesis. So your chemistry, you're probably wondering, how do you do that? How do you synthesize this? So basically, it's a core shell nanoparticle. It's a core shell system. In the core, you have these magnetic nanoparticles that, in this case here, they are behaving as local heaters, as heat spots. And on the top of this megamite, you have a polymer. So the key point here was the the development of this block polymer, which has these pyridine groups here, and these pyridine groups here, they have a preferential interaction with the surface of the iron oxide. And in these polymer chains, you can incorporate these europium and terbium complexes that gives you the information about temperature with their fluorescence. So this is basically what you're doing. That the megamite nanoparticles, it's a standard method. It's just you have iron salts in a water solution, and then you increase pH. And when you increase pH, you first form the hydroxides, and then you start condensing hydroxides, you release water, and you get an iron-oxygen-iron bond, and you have your nano iron oxide. So this is how we did this thermometric beads, these thermometrical nanoparticles. And we went to another design. So instead of that block polymer, we had a polymer here attached to a silica molecule. So this was a 3-hydroxysilane, and then we made this chemistry here, and we put this on the surface to try to be able to measure temperature in a surface like a PCB board, in a silicon surface, because all the things that we are producing in terms of computing are still based on silicon. And so that's what we were trying to do. We are trying to have a very nice thermometer, but in fact, we came up with something different. We came up with something that gives us, so this intensity of fluorescence has not a well-defined relation with temperature. So it has this thermal hysteresis. So it gives us information about temperature, but also information about the history of the system. So when we are heating up, so that's the response. Sorry, again, I lost where is my here? So when we are heating, we are on this curve here, we are cooling, we are going down here. And so this is somehow reminiscent of what nature does. If you remember what I just showed you a couple of slides before. So you don't have a well-defined relation between temperature and this physical property. In this case is current, in our case is fluorescence intensity, but you don't have this well-defined relation, and you have hysteresis. So we have here something which is more complex, and it's not a good thermometer in the sense that we can have a value which is unequivocally related to the present temperature, but we have something that has some sort of a memory that we went to a higher temperature, and then slowly it starts forgetting this memory. So it's something more complex, but also more interesting if we are able to extract information from that. And so we start having something related with memory. And when we talk about memory, I think immediately about magnets, because the way that we record information, one of the most efficient ways of recording information is using magnets, because magnets can keep a given direction, so you can keep up or down direction, so you can record zeros and ones, so you can get into the world of logic with zeros and one using magnets. So I was working with magnets, and so we start thinking about recording temperature with magnets. So using magnets not to record data as we do every time that we use a magnetic hard disk, but recording temperature. And this could be interesting, for instance, to understand phenomena which is really fast in time. If you don't have time to catch up with temperature, if we record a snapshot, you can see that snapshot later. So recording can be an interesting concept in the field of temperature. And so normally magnets, they are magnetic at room temperature, but we came up with these magnetic nanoparticles where they change their magnetic state when they cross 45 degrees centigrade. So basically they are magnetic below this temperature, and once you cross this temperature, they become non-magnetic, and then if you come back again, they become again magnetic. So you see them, they just go back to the magnet, they become magnetized. And they do that at 45 degrees Celsius. So again, it's something reminiscent of what happens in nature, something that has a click. It gets on and it gets off at this temperature here. So basically, the magnetic response is this one here. It has a high magnetic response below this 45 degrees Celsius, and it has a low magnetic response above this temperature here. So, and you can see this is a logarithmic scale. So this is a huge change of magnetization in a very narrow temperature range. So, and why can this be interesting? I give you this example, Thermodox. It's a drug that is already in the market, and it's designed, this drug is designed to release this doxorubicin at a given temperature threshold. So it's designed to keep the drug inside until this temperature is crossed, and then it releases the drug. So you can target, you can control where this drug is being released. And now, so our point is, you cannot really control in vivo if you don't know the temperature. So if you could have such a thing like a magnetic particle that gives you a response when you trigger this temperature threshold, though that would be interesting to control temperature in this relevant application. How do we do this? We synthesize these nanoparticles by thermodecomposition. So we have this iron polyate precursor, so it's the source of iron. We have a selenide octadecene precursor here, it's the source of selenide. We mix them with in an organic medium here. We control temperature here. We control the nitrogen. And then we make a temperature ramp. We stay there for some time. We control the ligands. The ligands control the reactivity of these precursors. And we get these nice nanoparticles with these organic ligands here at the surface, if you can see them. So then we can also take them from the organic solvents to the water solvents by using this chemical chemistry here. And so we get this really nice, from my point of view, nanoparticles with these controlled magnetic properties. So I see Professor Veronica already there, so it means that my time is up. So let me just, bring you, we are also making these nanoparticles inside capsules, polymer capsules. We are putting them inside cells. So we are making the other way around. So one way we are trying to think like nature thinks, and on the other way we are trying to get into nature the way we think. So inserting magnetic recording inside cells, giving these concepts of magnetic recording into cells, that's what we are trying to do now and in the future. So here we are developing these new ferrofluids, which are both ferrofluids and transparent. Here you can see across this ferrofluid, and you can see that still they are quite magnetic. So these are probably the most magnetic and transparent fluids of the world here. So this is what we are doing now. I will skip the chemistry and I will just give you this overview. In short, we are making this path from 0 dimension to 3-dimensional thermometers, and we are also making this path from the typical concepts of a reversible thermometer to new concepts of reversibility and of recording the recording temperature inside cells. So thank you very much, and Professor Veronica, the floor is yours again. Thank you.
Thank you very much, Nuno. I wasn't expecting otherwise, this marvelous talk. I haven't received any questions, so I do have one question. If you can be if you can answer briefly. So these amazing sort of carriers that you mentioned that you named as core shell carriers, which have the megamite inside, then they are covered with the European and terbium compounds. My question is, how do you put them into the body locally in situ in the place you want to? With an injection, with a solution? How do you do that, Nuno?
It's an interesting question because it goes into the target drug delivery. So it's a really important business to target drug delivery. People normally think, okay, this is magnetic, so you can do this magnetically. It's not that easy to do this magnetically. I think in the quest for drug delivery, chemistry is much better than magnetism in the sense you need to have here some target. You need to have here some antibodies. You need to have here at the surface some targeting molecules because van der Waals interactions, so chemical interactions, are much stronger than magnetic interactions. You can accumulate things inside the body with magnetism. There was in fact a company dealing with this, but you need some special tools. For instance, this company was devoted to target particles and cells to inside veins. But they had something which was like a magnetic grid inside. Okay, and so by having that, you could have magnetic attachment. But by playing just outside the body with magnets, it's really difficult to target and to get these things where you really want. So chemistry is the answer again for this target drug delivery.
So the key lock principle in the end.
Key lock principle of chemistry. It's a strong principle. It's a really strong principle. We think that magnetism is strong, and it is, but chemical bonding is much stronger than magnetism. So I think chemical bonding is the key chemical interactions.
Okay, thank you very much, Nuno, for your enlightening
Thank you.
answer. And I thank both speakers, Professor Paulo Ferreira and Dr. Nuno Silva. Thank you very much for being with us. I think you probably enjoyed as much as I did with these two very interesting talks. And now I would like to go and visit and enjoy the poster session. Thank you very much.
Hello, good morning, everyone, again. So let's begin the second session of today's morning. I will give the word to Professor Rui Fausto, that will be the chair of this session. So see you soon and enjoy.
Well, good morning to everybody. Thank you, Inez, and all the organizers for having invited me to chair this session. It is certainly a great pleasure. And the session will have 3 oral talks plus an invited lecture. And the invited lecture will be delivered by Professor Rita Bacelar Figueira from the University of Minho. And the talk will be dedicated to the memory of Professor Carlos Jorge Ribeiro da Silva, that was a member of this scientific committee at the meeting, and that unfortunately passed away on August 27th, very unexpectedly. So I will immediately give the word to Professor Rita Figueira. Rita graduated in chemistry in 2002 and obtained his master's degree in technological chemistry in 2008 from the Faculty of Sciences of the University of Lisbon. And then she obtained her PhD at the University of Minho. And later on, she started to work as a research fellow at the NEC until 2017 at the Department of Materials. Then she got a junior researcher at the Center of Chemistry at the University of Minho, and her research interests involve the synthesis and characterization of sol gel materials for corrosion and sensing applications. She has also interests in electroreduction of CO2 in gas phase. And currently, Rita is research coordinator at VG Collab Energy Storage Group. And please, we are looking forward to listening from you.
Thank you very much for the presentation. And thank you very much for the invitation to be here today and all the people involved in this meeting. Everyone is seeing my...
That's okay.
Okay, thank you. Hybrid sol gel membranes to apply on optical fiber sensors and to monitor the durability of concrete structures. First of all, I will do a brief introduction about sol gel, and there's a lot of definitions about sol gel, and the one that I identify most, it's the one about according to Pierre, where every process that starts from a precursor solution with intermediate stage, including a gel and or a sol. You can see the two reactions, an hydrolysis reaction and condensation reaction, that are involved in the sol gel synthesis of hybrid sol gel materials. The sol gel method involves several steps. First, we need to choose the precursors. Then we obtain a sol, then a gel, and then we have the step of drying. Depending on the step of drying, we can obtain aerogels, monoliths, chiral gels, films, or fibers. And depending on the precursors you choose, you are able to obtain organic, inorganic hybrid matrices. In this slide, you can see several examples of application of sol gel materials. For instance, you can see application of sol gel materials in coatings, in sensors, as smart materials, in biomedical field, in optical field, and in green technology. One of the main advantages of this process is that allows you to obtain, at mild conditions, a wide range of materials. This type of materials can be classified in three classes. The first class, it's known by the materials that establish between this classification is based on the type of bonds established between the organic and inorganic components. When you have an organic component interacting with the inorganic component by hydrogen bonds or van der Waals forces or ionic bonds, they are classified as class 1. If you have organic components linked to inorganic components by covalent bonds, you classified them as class 2 salt gel materials. And if you have a mix of both type of bonds, you can classify them as class 3 salt gel materials. An example of class 3 materials is when you have, it's a kind of hybrid where the material is obtained by an organic polymer containing hydroxylable alkoxysilans and hydrogen acceptor groups, such as carbonyls, amines, and imides. This slide shows you the schematic of synthesis, the materials that we produce at UMinho University, where you can see we obtain this type of hybrid salt gel materials and are class 2, are classified as class 2 materials. So the project we are developing, and I'm here to talk about a bit of the project developed together with Professor Carlos, was born from his knowledge and my knowledge. So I worked back then in the National Laboratory for Civil Engineering, and I was linked to the degradation of concrete structures, and he was involved in the synthesis of salt gel materials. And when we talk about the degradation of concrete structures, we have two types of pathologies that attack the structures. One of them is alkali-silica reaction, that I'm going to speak easily as ACR, and the other one is corrosion of reinforced concrete. That can be due to carbonation of concrete or due to chloride ions. So the alkali-silica reaction only takes place in certain conditions. There are 4 main requirements that must be simultaneously satisfied. The existence of reactive aggregates with concentrations within a critical range, such as the source of reactive silica, high alkalis concentration, or more precisely, high hydroxyl ions concentration in the interstitial concrete pore solution for silica attack. You have to be also a source of calcium, soluble calcium, such as portlandite, to react with the dissolved silica and form a deleterious gel. And finally, you need to have moisture. When you have moisture, that gel will expand, and after expanding, he will lead to the formation of such cracks like this. You can see in this picture. In this figure, you can see this 3 stage of alkali-silica reaction taking place. After the gel expands, the crack occurs. So the degradation caused by reinforced concrete corrosion can be due to the carbonation of concrete, due to carbon dioxide presence, or due to the presence of chloride ions. You can see here cases of structures damaged by chloride ions. The main problem is that the rebar that is inside the concrete expands due to the formation of iron oxides, and due to that expansion, it leads to cracking of concrete. And after that, the concrete detached, and you stay with the rebars completely exposed. This will lead to a consumption of the iron, which lead to a loss of section of steel, and in extreme cases, this can lead to the collapse of the structure. So here I'm going to show you detail of how the corrosion in concrete initiates. You need to have water, carbon dioxide, and if you have carbon dioxide, you can start by having concrete carbonation. And as the carbon dioxide reacts, forming the calcium hydroxide, you will have problems, and then the concrete no longer protects the steel, and the pH drops to values. Normally, the pH of concrete, it's between the healthy concrete, it's above 12. And when the concrete starts to degrade by carbonation, it falls to values between 6 and 9. In these schematics, you can see that the carbon dioxide may attack the concrete, and after that, you have chloride ions entering inside the concrete structure, and then the corrosion process initiates. So with these two science, the sol gel and concrete degradation structures, we thought about the development of a project that is Sol Sensors project, which was composed by 3 institutions, Inestec, Solsense, University of Minho, and a small medium enterprise from Alentejo. And after that, we started a new adventure at UMinho. And I'm going to show you a video, and I'm sorry because it's in Portuguese. I don't know why I can't access to this, but I will try go in here. Should be in here, where you can have a first glimpse about the main objectives of the project. It's not working. Let me try again.
Hoje em dia, verifica-se um envelhecimento e degradação prematura das estruturas de betão e betão armado. A consequência são elevados custos de reparação, manutenção e reabilitação. A principal causa desta deterioração e redução da durabilidade estrutural é a corrosão das armaduras. Por mais resistente que a estrutura seja, a corrosão pode levar ao seu colapso, como aconteceu em 2018 na Ponte de Génova, causando 43 mortos. Ainda assim, a indústria da construção civil continua bastante tradicional e com alguma resistência à inovação tecnológica. O projeto Sol Sensors nasce para contrariar essa tendência. A ideia é desenvolver o protótipo de um sensor multiplex que será embebido em betão. Nada mais, nada menos.
Instead of sharing the application, you have to share the screen of your computer.
I will try to start all over again. I will just I have to stop sharing this, start sharing.
Hoje em dia, verifica-se o envelhecimento e degradação prematura das estruturas de betão e betão armado. A consequência são elevados custos de reparação, manutenção e reabilitação. A principal causa desta deterioração e redução da durabilidade estrutural é a corrosão das armaduras. Por mais resistente que a estrutura seja, a corrosão pode levar ao seu colapso, como aconteceu em 2018 na Ponte de Génova, causando 43 mortos. Ainda assim, a indústria da construção civil continua bastante tradicional e com alguma resistência à inovação tecnológica. O projeto Sol Sensors nasce para contrariar essa tendência. A ideia é desenvolver o protótipo de um sensor multiplex que será embebido em betão. Nada mais, nada menos que uma forma de verificar a saúde das estruturas de betão e betão armado.
Resumindo, este tipo de sensores baseados em fibras ópticas acoplados a novos materiais híbridos que serão sintetizados pelo método Sol-Gel irão permitir monitorizar vários parâmetros.
Parâmetros como o pH, a umidade, o teor de íons sódio e potássio e a entrada de agentes agressivos no betão de recobrimento, como os íons cloreto. Reduzir custos através do conhecimento aprofundado do desempenho estrutural e dos requisitos de manutenção e conservação é o que se pretende. No fundo, uma abordagem mais racional de recursos, nomeadamente a estimativa das opções de reparação, assim como o agendamento das estratégias de inspeção e manutenção. Será o primeiro sistema a monitorizar em simultâneo o pH, a umidade, os íons cloreto e as reações álcalis-sílica. A informação recolhida permitirá, assim, melhorar modelos teóricos e prever com precisão o comportamento das estruturas de betão e betão armado. No âmbito do projeto Sol Sensors, a ideia é acompanhar em tempo real como se estão a comportar as estruturas e, caso seja necessária uma intervenção, fazê-lo em tempo útil, protegendo o mais perene valor de todos, a vida humana. Este projeto vai apostar no desenvolvimento de novos materiais híbridos e em avançados sensores de fibra óptica, um protótipo inovador à escala mundial, em sintonia com os objetivos da Estratégia Europa 2020. Uma clara e incontestável aposta no crescimento inteligente e sustentável, com o futuro hoje.
So, back to the presentation. I hope you enjoyed and understand a bit of what we are trying to do, because it's a multidisciplinary work, so it's not easy for me to put it all together. So what we try to do here is to develop, sorry. What we are trying to do here is to develop sol-gel materials that are stable in alkaline environment and need to be a permeable matrix, and the signal, the detection of the species such as chloride ions, to detect the alkali-silica reaction, we need to detect moisture, detect potassium ions and sodium ions, and pH also, because to control the carbonation concrete, we need to control the pH. And then we put it, everything, the membrane, in the optical fiber. And then the optical fiber will answer by changing the refractive index or by answering with a colorimetric or a fluorometric answer. It depends on the membrane that we use. So, chloride ions for corrosion, sodium, potassium, and moisture for alkali silica reaction, and carbonation of concrete. We monitor the pH. Today, I'm going to talk only for pH detection. The first approach we used was to develop polydimethylsiloxanes material, sol gel matrix doped with pH species sensitive. We used as precursors polydimethylsiloxane diglycidyl ether and 3-aminopropyl trimethoxysilane or 3-aminopropyl triethoxysilane. It depended in what we used. We used always PDMS, and then we changed APTMS or APTES. And then we used as chemical transducer the phenolphthalein, a widely known indicator. The synthesis process that we used for this first approach is here represented. We made react PDMS with 3-APTES, and we obtained this precursor. We used as catalyst acid citric in ethanol, water, and we let it cured for 15 days in an oven at 40 degrees. So we produced samples with a ratio of aminopropyl silane to PDMS of 2 and 2.5 and 5 and 7. The higher ratios did not give good results, so I'm not going to discuss it here. And the lower ratio we used with different contents of phenolphthalein. we prepared with aminopropyl silane and with aminoetoxysilane. What you can see here, it's the absorbance obtained for the different films, hybrid films prepared. You can see that there's a constant absorbance within a range of 400 to 800 nanometers. And it's possible to dope in this range with colorimetric compounds. So we doped with phenolphthalein. Here you can see the plot absorbance for phenolphthalein. And as the concentration of phenolphthalein you used, the absorbance increased. So we tested with different environments in acidic media and alkaline media for all the samples synthesized. And you can see that as increase the contents of phenolphthalein, the peaks increase. However, the difference between when we used alkaline media and acidic media was more intense with higher concentrations of phenolphthalein. Then we measured and analyzed by electronic impedance spectroscopy in simulated concrete pore solutions. A simulated concrete pore solution is a solution that simulates the pH inside the pores of concrete, where we use carbon, it's a saturated solution of carbon hydroxide, calcium hydroxide, and hydroxide potassium. And it's a pH above the 12. And you can see that as the time passes, the profiles of the impedance changes. This means that the material is deteriorating. As you can see, the resistance is decreasing within the time. We obtained similar results for all the matrices. Also, we saw that the matrices aminopropyl prepared with the same PDMS and different precursors, aminopropyl or aminoethyl siloxane, show a different profiles with using electrochemical impedance spectroscopy. So the results obtained with this study allow us to conclude that the dielectric film's property changed through time in the alkaline environment. The films can be doped with colorimetric sensors in the range between the 400 and 800 nanometers. The phenolphthalein did not affect the optical or dielectrical properties of the films, and no optical change for the phenolphthalein, the films doped with phenolphthalein for 30 minutes in acid and alkaline solutions were found. So we changed to another precursors. We started working with jeffamines and made it react with 3-glycidoxypropyltrimetoxysilane, that I'm going to just say GPTMS, it's easier. And we obtained such films. We maintained always GPTMS, and we changed the jeffamine. We used jeffamine EDR 148, jeffamine T 403, jeffamine RFD 270, and SD 2001, and THF 170. The difference between these jeffamines, it's the molecular weight between SD 2001 and THF and 117 and EDR 148. These two, this as a ramification and this as an aliphatic in the middle, a ring. So you will see that this difference is reflected in the properties. So when we use the ultraviolet spectroscopy, visible spectroscopy analysis, we saw that the transmittance changed with the different jeffamines. You can see that the samples prepared with jeffamine 2001, SD 2001, we name it A because the type of bond established between the jeffamine and the GPTMS, it's an amino alkyl bond, showed the lowest transmittance, and the one with the highest transmittance, it's A403. As you can see it here, this is the lowest transmittance and this is the highest transmittance. So we also studied the samples by electrochemical impedance spectroscopy, and we performed adjusts to the equivalent electrical circuit and made the fitting and obtained the following results. You can see here that generally, as the molecular weight of jeffamine increases, generally, the normalized resistance decreases. There's a difference between for A270 compared to A400, and this may be due to the fact that the RFD 270 contains an aliphatic amine containing both rigid cycloaliphatic and flexible heteramine segments within the same molecule. So this may explain these differences. Because the previous studies that we performed with also similar products that establish the same type of bonds, you see that as the molecular weight of jeffamine increases, the resistance decreases. And this is directly connected with the content of organic component. So it's something that we were expected to obtain. Then we assessed the materials in mortars. The mortars were prepared with the water cement ratio equal to 0.5. You can see that after 7 days, only the sample obtained prepared with Gefamine 170 A170 showed good results. The others reacted or were completely destroyed due to high alkalinity of the cement paste. So we started working only with Gefamine, THIF 170 and GPTMS. After 28 days, the same behavior was found. A403, we only found remains, and A270, you can see some parts of the films, but it was completely destructed. So you can see that the sample A170 that we extracted from the mortars after 7 days decreased in the thickness 3.70%, after 14 days 1.27%, and after 28 days 0.22%. In the end, we can conclude that we obtain hybrid salt gel materials based on amino-alkyl silicate matrices that were crack-free and homogeneous, but and the different Gefamines influenced the optical and electrochemical properties. The lowest and highest transmittance was between 400 and 700 nanometers were given by A2001 and A403 respectively. And the capacitance values, I did not spoke about before, were lower than the ones already reported for similar materials. Only samples prepared with Gefamine 170 are resistant to highly alkaline environments. Samples in contact with cement paste, the samples A170 that were in contact with cement paste show promising properties that support films in optical sensors fields to be applied in civil engineering fields, and A270 and A403, despite interesting optical and electrical properties, are not suitable for highly alkaline environments. The second approach included to use phenolphthalein using the matrix already reported, and we use CTAB. We prepared the synthesis with CTAB and without CTAB. You can see here the samples prepared and without being in contact with the simulated concrete pore solution at pH above 12. I'm sorry. And you can see here after being in contact with simulating concrete pore solutions. As you can see, the undoped film does not show any change. The doped film with the phenolphthalein species shows changes when in contact with simulated concrete pore solution, as well either using or with or without CTAB. From the spectroscopy analysis, we see that the presence of CTAB gave us a decrease in the transmittance that is indicated by these values here. And we have, when we use phenolphthalein, we have a decrease compared to samples without phenolphthalein. So the data obtained for the films, you can see there's a difference between the resistance with and without phenolphthalein, and CTAB also influences also influences the resistance of the samples. The main conclusions that we reached with these studies were the hybrid samples with pH sensing ability were successfully synthesized by using the precursors GPTMS and Jeffamine THF 170 as precursors, and CTRB and phenolphthalein as doping materials. The transmittance of the synthesized hybrids decreased after doping with phenolphthalein, and even more when CTRB was present. The incorporation of CTRB and phenolphthalein in the hybrid matrix did not affect the chemical structure. The pure matrix show lowest resistance values. The resistance of the two dope matrices are between these values, and the values of permittivity are between 10.30 and 10.54, which are higher than the pure matrix. The properties, we concluded that the properties show suitable, the films show suitable properties to be used for concrete sensing purposes. So in the third approach, we continue to use Jeffamine THF 170.
You have 3 minutes.
How many?
About 3 minutes.
3 minutes, okay. And we tested some imidazole derivatives. You know, this type of materials are amphoteric, so you can see the changes in optical properties, and they can act as chemosensors. I will show you these pictures. In pH 9, you see something like this. At pH 12.5, you see this. This is a fluorescent material. This is a colorimetric material. So we doped the same matrix with this. And we obtained stable matrices. I will not go further in this because I have something that I want to share more personal about Professor Carlos, for those who know him before. And if you want to know more about our project, you can contact me. We performed always the same studies. We performed electrochemical impedance, FTIR, and we concluded in the end that the imidazole derivatives showed colorimetric, fluorimetric changes. The doped hybrid sol-gel materials was successful, and the presence of imidazole derivatives was shown. And they have potential to be applied as pH sensors. Me and Professor Carlos had a big journey. We were colleagues, we were friends, and I want to share this video with you. And I hope you enjoyed my session. Thank you for your attention. I hope I can take it on time.
Thank you, Rita, for your talk and also for sharing with us his memories of Professor Carlos Silva. So we have about 3 minutes for questions from the audience. Okay, I will so ask you a question that is, the materials look pretty interesting, but as far as I could realize, still you are trying to find a way to make them more stable in the conditions you want to use them.
Yeah.
Can you open a little bit um, uh, your thoughts to us and share with us what are the things you have in mind to try to improve the stability of the materials in the place they are supposed to be.
We need to incorporate more inorganic component, because when we have more inorganic components, we increase the resistance to high alkaline environment. And at the same time that we incorporate the inorganic component, this is decreasing the chain of organic components and increase the inorganic component content within the hybrid material. And then the problem is when we increase the inorganic component, we lose permeability. So we need to increase the inorganic component, and then we work at high pressures to open the pores of the matrix to allow the analyte get in and to detect it. So that's what we need to try to do now.
So this last material you showed us, which is the time it can survive in the material?
This one that we have that is stable, he survived 28 days, he will survive a life, I believe, because after concrete get cured, the pH stabilized and the reaction stabilized. You will not have more reactions. If we get a material that is stable for 7 days, 40 days, he will be stable within the concrete for 20 years. I believe that. If we have a more inorganic material with high porosity that stands 7 days, we have the problem completely solved.
Thank you very much. Are there any questions? So Rita, thank you very much. I think we shall thank you for your talk, and we shall move to the next.
Thank you very much.
Artur, I don't know if you want to introduce the next speaker. Are you there, Artur? Doesn't answer. So I will introduce the next speaker. Myself is Marcos Bento from the University of Lisbon, and you will present a talk on the CO2 reduction with format dehydrogenase mimetic compounds. So the stage is yours, Mark.
Thanks for the kind presentation, Rui. So today I will talk about the work that I developed during my master thesis over the last year in the area of CO2 reduction catalysis. So as you probably know, climate change is one of the biggest threats for human life, leading to several implications to our world, such as sea level rise, extreme weather conditions, and increased precipitation. This environmental change is directly related to the greenhouse effect and to the emission of greenhouse gases to our atmosphere, which, once trapped in our atmosphere, absorb and emit infrared radiations toward the Earth's surface. One of the most emitted gases to the atmosphere is carbon dioxide, and in the last years, the concentration levels of this greenhouse gas reached up to new historical records. For this reason, researchers are searching for new ways to struggle this problem. One of the approaches used as a solution for this environmental problem, it's carbon dioxide conversion. And carbon dioxide conversion consists in the reduction of carbon dioxide into new added valued products that can be used as a chemical feedstocks or fuels. The most common products are methanol, methane, formate, and carbon monoxide. There are several ways to do this type of conversion, but for me, in my point of view, the most interesting way it's using photo and electrochemical techniques and using renewable energy and different types of catalysts to do this conversion. Recently, the researchers are searching for new types of catalysts and are getting inspiration in different types of molecules and complex structures present in the nature, such as enzymes. One enzyme capable of doing this type of conversion it's format dehydrogenases. This enzyme does the reversible reaction between carbon dioxide and the formate. It's constituted by two pyranopterin cofactors coordinated to a molybdenum center, and this metallic center is also coordinated to a sulfur atom and a selenocysteine residue. In the neighborhood of this metal center, we can also observe an histidine and arginine residue that are part of the catalytic center of the enzyme. For this reason, we based on format dehydrogenase and in pyranopterin cofactor to synthesize new ligands and new molybdenum complexes as a catalyst for CO2 conversion reaction. We are interested in different types of catalysts, but in different types of ligands, but most of the ligands are based on ethylene groups. Today I will talk about the one ligand from the PPAS2 family and was synthesized through substitution reaction of the chlorodiphenyl phosphine with the hexamethyl disilazane, and the intermediate was reacted with atomic sulfur. The ligand was characterized through NMR, FTIR, UV, and elemental analysis. I will show you just the NMR characterization once the ligand was already published. So to characterize the ligand, we did some proton NMR experiments, cozy experiments, and phosphorus NMR experiments. To do the complex synthesis, we react the ligand with molybdenum hexacarbonate under inert atmosphere, building a air-sensitive compound that will be tested for CO2 conversion. So we characterize the ligand through NMR techniques, FTIR, UV, elemental analysis, and finally, after confirming the purity and of the compound, we did some electrochemical studies in order to understand if this compound can be a good catalyst for this type of conversion. So I will start to show you the NMR characterization, and we did some proton NMR experiments, cozy experiments, carbon NMR experiments, and the heteronuclear experiments that led us to confirm the overall structure of the molecule. The FTIR characterization was very important to observe the vibrational mode of the carbonyl ligands binded to the metal. And after all this characterization, we did some cyclic voltammetry studies. So, firstly, we did a cyclic voltammetry study under carbon dioxide, which indicates that which demonstrates an increase of the current and indicates that this molecule can be a good catalyst for this type of conversion. Through the addition of different water concentrations, we observe also an increase of the current, which can be indicative or that water can enhances the conversion of carbon dioxide. In order to quantify and detect the different products of this conversion, we did some controlled potential electrolysis experiments, and through the analysis of the current time graphic, we can see a decrease in the current, which indicates catalyst degradation. This can be also confirmed through the difference in the linear voltammograms before and after the electrolysis experiment. For the detection of the products, firstly, we analyzed the headspace of our electrochemical cell through GCTCD, and we didn't see any kind of gaseous products for CO2 conversion. By the analysis of the bulk electrolysis solution with maleic acid standard solution and using a multiple solvent suppression experience, we detect some formic acid that was formed during the electrolysis. So finally, we can conclude that the ligand and the complex was successfully obtained in high purity. The complex was catalyzed the reduction of the carbon dioxide into formic acid in the presence of 850 millimolar of water. The NMR method used in this work allowed to us detect formic acid. The synthesis and the crystallization methods will be improved in order to obtain high yields of the pure catalysts. The formic acid will be quantified using an improved NMR experiment and Ionic liquid chromatography. And finally, the mechanistic pathways of this reaction will be studied through spectroelectrochemical techniques. Finally, I want to thank to FCT for funding our project, to Dr. Paulo Martin, Dr. Luisa Maia, Professor Paula Brandt, Dr. Marta Saraiva, Dr. Sara Realista, Professor Maria José Calhorda, my lab colleagues, and to you and the organization committee for letting me present my work. Thank you all.
Thank you very much, Marcus, also for keeping on time. So we have time for a few questions. So Marcus, let me ask you two simple questions about your work, that is certainly very interesting. The first one is, have you determined the yield of your reactions, the reaction for the transformation of the CO2 in formic acid?
No, we didn't quantify the product, so we didn't. We didn't was when unable to quantify to calculate the yield of the reaction, but now we are working in the for quantificate the formic acid and to do all the calculations of selectivity, bonds, DOF, and yielding of the reaction.
So I suppose you choose to present us these results using this catalyst because it is probably the best one up to now that you have investigated.
Yes, but was very difficult to put all the catalysts here. So yes, I choose this because it was a little better than the others, and because in the others we also have to do some extra characterization. So Yes.
Okay. May I ask you also, what is the cost of these materials? I mean, I'm thinking in terms of the economical viability of the process. Are these materials expensive, or
I
by
think
the contrary, are they relatively cheap and they can really be considered as a potential?
I think not, because we don't have many reactional steps, but the most difficult way to improve this process, it's where we are in the scale up for the reaction, the electrochemical conversion of the reaction of the electrochemical conversion of carbon dioxide. But I don't know, it will be more studies, and after we can discuss
Sure.
this.
It's a very competitive area, I must say.
Yes.
So any questions, any additional questions?
I think Professora Rita Barcelar has a question.
Okay, Rita, please, go ahead.
What is your next step here? What do you intend to do next? If you can say.
We are now, the next step is understand the mechanistic pathway, and try to quantificate the formic acid generated during the reaction.
Are you doing DFT studies to complement the results, or no, or not?
Yes.
Okay, and they are in agreement with your results?
We didn't did some of these studies, but it's the next step. It's to do these studies. So, but we didn't have results yet.
Okay, so I think you should go there. That's the future.
Okay, thank you.
Find the number of redox pairs and see where you can go with the modeling. It will spare some time.
Okay, thank you.
Okay, sorry. Thank you, Professor Rui Fausto, for covering me while my computer was crashing. And thank you again, Mr. Marcos Bento, for your presentation. And now we can move on to the next speaker. I remind you that you have 12 minutes. Mr. José Roque, who comes from CQC, and he'll be talking about H tunneling activated upon vibrational excitation. So please, the floor is yours.
Thank you very much. Can you hear me and see the slide? Okay.
Yes, we see.
Thank you. Thank you for your kind introduction. My name is José Roque, and I will now present some recent developments over my PhD studies. In particular, an example on how to activate a tunneling reaction upon vibrational excitation. And so the reason we got interested in these hydrogen tunneling reactions in the first place was because we were studying reactive intermediates such as radicals, carbocations, carbines, nitrines, among others. And of course, these molecules are very reactive, and their lifetime is very short under conventional laboratory conditions. But still, some groups try to characterize them through the use of time-resolved spectroscopies. But in our research group, we actually take an alternative approach, which is to try to enhance their stability and therefore their lifetime by using a method called matrix isolation. And the point with matrix isolation is to prepare a sample where our substance being studied is completely surrounded by an inert gas like argon, krypton, or nitrogen. And also this sample is prepared at extremely low temperatures, close to 0 Kelvin. But still, some of these molecules were found to undergo chemical transformations, and they do so by a mechanism called quantum tunneling. And basically, quantum tunneling predicts that a molecule being held in a deep well can actually penetrate a potential barrier to a different state, even though it lacks enough thermal energy to overcome the barrier classically. And so this tunneling probability for an inverted parabolic shape is given by this equation, and it depends exponentially on the barrier height, the barrier width, and also on the mass of the particles moving along the reaction coordinate. And on this topic, very exciting studies also shown that some molecules that react by quantum tunneling, they react in a conformer-specific fashion. For instance, these hydroxycarbons, when the molecules adopt an anti-conformation where the hydrogen group is close to the carbon center, they undergo chemical transformation to aldehyde products. But when the molecules adopt the syn orientation, they do not react at all. And in these real nitrines, depending on the orientation of aldehyde groups, either anti or syn orientation, there are two completely different reaction paths, either hydrogen migration or enclosure. In addition, our group has also been involved in this topic of infrared-induced chemistry, where it is possible to induce a chemical transformation by exciting specific vibrational modes. Namely, OH stretching modes can be excited, and when we excite these OH stretching modes, for instance, for the second excited vibrational state, the amount of energy that we are introducing in a molecule must then be dissipated to the environment, and this energy is released through a mechanism called intermolecular vibrational redistribution, where this excess of energy is distributed to many other vibrational modes. And if it lands on the reactive coordinate mode, which in this case is the torsion around the CO bond, it can actually populate both conformations, both syn and anti. So as a result, it is possible to convert syn conformers to anti-conformers. And so our goal in this project was to actually merge these two concepts of conformer-specific reactions in a way to control conformations, and to show that it is possible to activate a tunneling reaction if we indeed can control an unreactive conformer and transform it in a reactive one, which will then proceed to the final product spontaneously. And so, of course, to try to evaluate our hypothesis, we had to select a chemical model, which was based on some research done in 1996, where two independent groups show that an orthoazidophonol can be photoconverted by irradiations at 255 nanometers to an aminoketone, and that this particular transformation, even though they never found this intermediate, they suggested that this transformation should be intermediated by a nitrine species. And the reason we believe now that they couldn't find this nitrine is because the OH group is very close to the nitrine center, and therefore allows a fast migration of the hydrogen atom. So our proposal was to introduce a fluorine atom adjacent to the OH group, which should stabilize the anti-conformations through an intermolecular hydrogen bond. And from there, we would proceed to produce the anti-nitrine conformations by irradiations with UV photons, and also then use vibrational excitation to convert the conformer for a syn orientation, which would eventually react spontaneously to the final product. And we also did some early calculations at CBS KB3 level for both azides. And what calculations predict is that the Boltzmann distribution for the non-fluorinated derivative here in black, the Boltzmann distribution predicts that 99% of the molecules should adopt the syn-OH conformation. But when we introduce the fluorine atom, there's more or less 30% of the molecules here in green that should adopt anti-OH, which are the ones we are interested in. So this seemed like a very promising system. And indeed, we advanced with it, and we began our studies by synthesizing this azide, by treating an aniline derivative with sodium nitrite and sodium azide. And after the synthesis, we characterized this molecule by stationary infrared spectroscopy, by preparing a matrix with our substance and the nitrogen gas at 10 Kelvin. And in this slide, you can see the OH stretching vibrations, both the fundamental and the first overtone, the experimental spectra and the theoretical spectra based on some DFT calculations. And what we observed was that there were two bands completely distinguished, one for syn OH and another for anti-OH. This later one also includes the overlapping contributions of two conformers, and we estimate that more or less 1/3 of the total population of this azide should have anti-OH conformations. So afterwards, we proceeded with the photochemical conversion of the azide by removing nitrogen gas by irradiations at 255 nanometers. And here you can see a different spectrum, which is a spectra collected before and after the particular irradiation. And so the bands pointing downwards correspond to bands of the reactants, which are the azide, of course, and the bands pointing upwards correspond to the bands of photoproducts. And it is possible to see that the most intense bands in the spectrum were assigned to the product in blue, the final product, the aminoketone, but still we were able to detect a very small amount of triplet anti-nitrine, which is the electronic ground state, is a triplet state. And so we were able to verify that indeed there's a nitrine intermediating this transformation. Of course, we then had to proceed with a more detailed characterization of this species, because we were later intending to excite its first OH stretching overtone. So we observed that in the fundamental transition of the OH stretching, there were a broad band observing between the two bands of the azide. And even though we could not detect the first OH stretching overtone based on some enharmonic calculations and on the fundamental transition, we inferred that there should be a band lie between the two bands of the azide and centered more or less around 6976 centimeters -1. So we once again tuned our laser. We tuned our laser at this frequency, and we irradiated our sample at this frequency to find out that we could indeed convert the anti-triplet nitrine to the final product to excitation of its first OH stretching overtone. And here you can see the different spectra once again. So the bands pointing downwards are bands of the reactants, the triplet anti-nitrine, and the bands pointing upwards are bands of the aminoketone. This is the experimental spectra that we obtain, and here is the theoretical spectra predicted based on some bacterial calculations. They match very well and leave no doubts that this reaction is indeed occurring. But during all these studies, we could never find the anti-conformer of the nitrine. And so to try to understand why we could never find this species in particular, we computed the potential energy surface around it. And then we computed tunneling half-life times for its hydrogen migration. And so because this species has a triplet ground state and the final product has a singlet ground state, the reaction can proceed by two different mechanisms, either in the triplet surface followed by intersystem crossing, or in a spin-forbidden fashion through a minimum energy crossing point directly to the singlet ground state. And so we computed both half-life times with the methods that include quantum tunneling contributions. And we found that for the reaction occurring through the minimum energy crossing point, the theory predicts an half-life time in the timescale of a few milliseconds, thereby justifying the elusive nature of this species. So to conclude, in this work, we were first of all successfully in showing that indeed there's intermediacy of a nitrine species in this phototransformation study many years ago. And second of all, that it is possible to activate the tunneling reaction by controlling over the conformations of specific molecules through the use of vibrational excitation. And we hope that this study, this demonstration will provide further developments in the field of, for instance, molecular switches or general reactivity, namely by quantum tunneling. I would like also to mention that this work is now currently under review for publication in the Journal of the American Chemical Society, and hopefully will be available soon for I and we to share with you. And of course, I would like now to finish by acknowledging my PhD supervisors, Professor Rui Fausto, Professor Peter Schreiner, and Dr. Claudio Nunes, and also other colleagues who helped in participating in collaborating in this particular work. Of course, Coimbra Chemistry Center, the University of Coimbra, and Fundação para a Ciência e Tecnologia for all the funding, in particular my PhD grant. Thank you all very much for your kind attention as well, and thank you for the scientific and organizing committee for having me. Thank you very much.
Thank you for your excellent talk. Okay, very interesting. I'm waiting to see if there are some questions from the audience at YouTube, because there's a time delay. But in the meantime, I must say this is kind of amazing that you can perform such controlled reactions in such a controlled way. I was wondering, can you use this, for example, for unexpected reactivity? I mean, you in the last slide you were saying like you can your objective is to use this in further tunneling reactions. I mean, can you actually use this? You know, introducing small groups, studying them theoretically, how it affects the reactivity, and how can you induce a simple rotation in a CO bond to, you know, get a reactivity where it shouldn't happen.
Yeah, sure. So this is one of the ideas we are trying to study. Is basically what we need for this to occur is that we need what we call an antenna. So in this case, the antenna is also the functional group that is arising, but it should not be. There's no need to be. So we can have some functional group here that is the reactive functional group, and all we need is an antenna where we can introduce vibrational energy. And this antenna can be an OH group, can be an amino group. So yeah, this can be extended to many other reactions.
There are, however, some limitations. I mean, the fact that you need to work in such a controlled environment and probably with very, very little amounts, I would say. What's the maximum amount that you need to work in order to get this, you know, to get the characterization of the delta absorbance at these conditions for infrared spectroscopy? Yeah,
the conditions are perhaps the main advantages. The disadvantages are actually, I mean, because of course we are working at 10 Kelvin. So when we try to increase the temperature, which should be our aim in the future, these rotations of conformers will stop being hindered. They will just occur spontaneously. Mm-hmm. So we'll somehow stop having some control over it. And in terms of the amount for our experiments, the way we prepare these samples is that we sublimate our sample slowly, and so the bands start increasing over time, and so when we have absorbance close to 1 or 0.8 or something, we stop and we close all our valves and stop depositing the sample. So in that sense, we have some control over the amount that we are preparing.
Okay, that's quite nice. Mm-hmm. I'm checking if there are no further questions, and thank you again for also keeping on time. Okay. Maybe we can move on to the last speaker of our session.
Okay, thank you once again.
Thank you. The next speaker or last speaker will be Mohammad Tariq, and he comes from, from my institution actually, from Nova University of Lisbon, and he will talk about ionic liquids as dual functional inhibitors for gas hydrates formation and growth. So please, the floor is yours, Mohammad.
Can you see the
Yes, we can see and we can hear you perfectly. So please continue.
Okay. Thanks for a kind introduction, Arthur. Just a moment. Thanks for the kind introduction, and hello all good afternoon. And today I'm going to present the results of an ongoing project funded by the FCT on the gas hydrates mitigation and promotion using ionic liquids. So to begin with, I would like to tell that means what are gas hydrates for those who are not aware about them. So gas hydrates are crystalline solids which looks like ice, and where the gas molecules are entrapped within the three-dimensional network of the hydrogen bonded water molecules. And they are generally stable under high pressure and low temperature conditions. And there can be different types of three different types of gas hydrates. Type structure 1, structure 2, and structure H, which mainly depends on the size of the polyhedral cavities and the size of the gas molecules, such as for example, methane, ethane, and carbon dioxide can form structure 1 hydrates. Propane and isobutane can form structure 2, and complex mixture like methane and cyclopentane and methane and neohexane can form structure H type of hydrates. So these hydrate formation is a bigger problem, very big problem for oil and gas industry, because for gas processing you are always going to the deeper sea now. So there these conditions, the ideal conditions for the hydrate formation exist. That means as you go deeper into the sea, you have low temperature, high pressure, and you always, whenever you are processing the gas, you always have some produced water available. So whenever you have all these conditions met, you started to form hydrates, and sometimes can clog the whole pipelines, and which can cause the disruption in the production of production, and sometimes can be lethal, fatal for the life. So that's why industries are spending sometimes 10 to 15% of the production cost, which can run into millions of dollars. So there are different techniques to mitigate the formation of hydrates. So one is the system heating, where you cover the whole line or insulate the whole line so that you can raise the temperature so that hydrate cannot form. Then depressurization, so you just depressurize the line so that you are always in the outside the boundary of hydrate formation. Sometimes the water removal or dehydration is one of the option, and the last and least and the best most viable option is the chemical additives, use of chemical additives which can inhibit the hydrate formation. And so these chemical additives are known as gas hydrate inhibitors, and they are different type of inhibitors. So the most classical one are the thermodynamic inhibitors, which are generally methanol or glycol. So they do the preferential hydrogen bonding with the available water, so that you don't have enough water available to form the hydrates. The problem with them is that you need to use them in very huge quantity. Barrels of methanol and glycols are needed, and glycol is very highly viscous, sometimes cause also problem and additional cost of pumping. So from the and also when you are putting this much amount in the sea, it can cause environmental concern. That's why from the last 2 decades, low dosage hydrate inhibitors are came into existence. And then low dosage inhibitors also can be divided into 2 types: kinetic inhibitors and anti-agglomerates. So kinetic inhibitors are generally water soluble polymers, which can be polyvinyl caprolactam or polyvinyl pyrrolidinone. And what they do, they will not shift the boundaries of hydrate formation. They will not stop the hydrate formation. Instead, they will reduce the rate of formation. But then there is another one is called type of LDHIs, which are known as anti-agglomerates. These are generally surfactants, quaternary ammonium or phosphonium. So they will allow the formation, but they will not allow the hydrate to stick together to form bigger chunks and clog the pipeline. So that's why ionic liquids came into existence, because we know ionic liquids are designer solvents, and they are made up of cation and a different combination of cation and anion, which can result into low melting point salts compared to the conventional salt, and they can have the properties of both salt and molecular solvents. So these are the obvious choice to use them for hydrate inhibitor. So although people already are using or testing for them hydrate inhibition, but the most studied one are imidazole and ammonium based. So, and recently amino acids and amino acid plus ionic liquids are also being tested, but amino acid based ionic liquids are not yet tested. And there is a need to prepare task specific and biocompatible ionic liquids to perform this work. So that's why we have synthesized these 4 ionic liquids, which are thiouronium bromide, ethyl thiouronium bromide, and hydroxyethyl thiouronium bromide, and imidazolium acetyl glycinate, and collenium acetyl glycinate. And we have used this experimental setup, which is called rocking cell apparatus, which is a very specialized instrument to test the formation of hydrate. So it can work with a standard pressure of 200 bar, and it can work in large range of temperatures. And we can perform 5 experiments simultaneously with a very low quantity of sample. We have used CO2 to form the hydrates. Most often, the natural gas contains up to 85% of methane, and that's why people generally perform these tests on methane. But there are different gas wells available even in Europe and in Southeast Asia, where the CO2 content in the natural gas is very high. And CO2 and methane both form type of S1 structure. That's why we have used CO2 gas for testing these ionic liquids. And we have used this isochoric pressure search method. So in this method, what we do, we rapidly cool down the system. We gas and liquid, and then afterwards we leave it isothermal for a longer time, around 12 hours in this case, and then we very slowly we heat it. So wherever these curves, cooling and heating curves met and intersect, this point is called the hydrate equilibrium point or hydrate dissociation point. So and here you can see that methane is forming hydrates at a higher pressure and compared to CO2. So this is the CO2 hydrate phase behavior in presence of 10 weight%. We have chosen 10 weight% because 10 weight% is generally the reference concentration where all the additives were screened. And we are always in between the Q1, Q2 in these two quadruple points, because CO2 can form different phases and hydrate in different ways. But we restricted ourselves into this region where you have always liquid water, hydrate, and vapor. And then first of all, we validated our method and our apparatus, and we found that it is very well in good agreement with the literature one. And then in presence of ionic liquids, 10 weight% ionic liquids, what we found that all ionic liquids are shifting this hydrate equilibrium towards lower temperature and higher pressure. But what is interesting here, that means we don't see any, we cannot distinguish which ionic liquid is working better or which is worst. Then we did the kinetic screening. For that, we use a constant wrapping method where the system was cooled down very rapidly with a cooling rate of 0.1 degrees centigrade per minute, and continuously it was heated. And then you can see that means wherever you see a sudden pressure drop, it's called nucleation point or onset of nucleation. And then the subsequent pressure decrease is called growth. And then simultaneously, when you are heating, you have the onset of decomposition, and then you have complete dissociation. Afterwards, we use the same solution to do the second cycle. So this will be considered as memory solution. So we assume that there are some nucleus of the hydrates still exists in the system. Then these are the results for onset of hydrate nucleation in presence of 1 weight% ionic liquids, because we want to propose these ionic liquids as LDHIs. So it should be in between just 1 weight% to 3 weight%. So for a material to be kinetic inhibitor, the onset of nucleation temperature should be lower than the water onset temperature. So here you can see that means all of them are showing and we performed this at 2 different pressure, 30 bar and 36 bar, because sometimes you can get different results, and that's what we also observed in this case. So at 30 bar, we see that means hydroxyl thiouronium bromide is showing the best results, and collenium acetyl glycinate is showing the least result. At 36 bar, only thiouronium bromide is showing the inhibition, the rest are showing promotion. Which can be because it has been reported several times that high pressure might affect the inhibitor's performance, and sometimes it could also be because the stochastic nature of the hydrate formation. But we don't see in the memory solution, we don't see any significant effect, because these memory solution also follow the same trend. Then we did the onset of hydrate dissociation. So LDI, many LDIs, they can reduce the rate, but they cannot stop the formation of hydrates in the pipelines. So for a good inhibitor, TOD values should be lower than the TOD of water, the onset of dissociation of water. What we saw, that means in all cases, even in fresh or in memory, all of them are showing lower values than the water. So that means all ionic liquids are decreasing at TOD, and that means the hydrates are decomposes easily in presence of these ionic liquids.
Mohammed, 2 minutes, please.
Yes. So hydrate growth. Then we normalize the pressure from the nucleation point onwards, and we saw that means at 30 bar the results were not conclusive. So that's why we presented the results at 36 bar. What we see here, that two of the ionic liquids, which are amino acid based ionic liquids, are showing higher growth compared to the thiouronium one. So it can be because many ionic liquids, amino acid based ionic liquids, are known to solubilize CO2 very well. And then in case of hydrate decomposition, we saw that all the ionic liquids containing solutions are decomposed much easier compared to uninhibited system. So at the end, I would like to conclude that ionic liquid can be proposed as potential dual function inhibitors, because at 10 weight percent they can be they can act as thermodynamic inhibitor, but they are mild inhibitor. And ionic liquid also can show kinetic inhibition efficiency at just 1 weight percent, but it is very highly pressure dependent. Similarly, apart from delaying the nucleation, the thiouronium ionic liquids are inhibiting the growth rate of hydrates. And then thiouronium hydroxyl bromide is clearly the best inhibitor, delaying the hydrate nucleation and suppressing the hydrate growth. So in future, we are going to use some NMR experiments, high pressure NMR and molecular dynamic simulation to understand the mechanism of inhibition. And also more amino acid based ionic liquids are currently under study in our laboratory. And last but not least, but I would like to thank the Fundação para a Ciência e Tecnologia for the grant of the project, LAQV, and my colleagues and mentors, and lastly to the PYCHeM for giving me the opportunity. Thank you very much.
So thank you, Mohammed, for your talk. And I was just going to wait for your video to finish on the YouTube feed in order to see if there are some questions. But I can just ask a very short question. So in summary, you are going to invest in amino acid ionic liquids. That's what I understood.
Yes, our goal is amino acid based ionic liquids, yeah.
But any specific amino acid, can you predict, how they behave if you have just a small alanine, or if you have like a phenylalanine or something like this?
It's very difficult. Right now, yes, phenylalanine is very known inhibitor, promoter basically, not inhibitor. Okay. But the problem is that means it's the hydrate formation phenomena is very stochastic in nature. So it's very difficult to predict it. Thermodynamic inhibition you can predict, but formation is always a problem. So because it's nucleation. So nucleation is very difficult to predict.
And in these conditions, right?
Yes. And then you have different temperature conditions, different pressure conditions, and also you don't have any, sometimes what happened that the driving force for hydrate formation is the initial pressure and the subcooling, how low you are going from the equilibrium where the hydrate can exist. And that can also, and in big systems, it's very difficult to maintain. So there are people who are working where they have a instrument, even without inhibitor, presence of any inhibitor, it's very difficult to predict, even for CO2, when the nucleation is occurring. So nucleation occurs somewhat before, but what you are seeing is the induction time. I can show you. Yes. So here, as you can see, when you are cooling the system. So the temperature, the pressure is also going down because the temperature is going down. And then afterwards, you have a sudden drop in pressure. So there is the nucleation point, but it's not really actually a nucleation because nucleation occurs somewhat before that. So it's quite difficult to know the exact point. So that's why we talk always in terms of this onset of nucleation.
So there's no data yet on the theoretical point of view. I mean, computational models can be used and you are going to do it, but you still haven't found the time yet. Okay. Yeah. Let me see. From the YouTube feed, there's nothing. I don't know if somebody of the guests wants to add something.
I think we shall thank the speaker.
Yes, let's thank the oral communications and also Professor Rita Bacelar Figueira for her talk, and everybody who has been listening to us in the YouTube channel. Thank you for attending, and we'll see you. We'll reconvene. I don't know at which time. I need to check.
2:30.
At 2:30. No.
Isn't it?
Yes, you are correct.
Okay. Yeah, I saw the.
Yes.
I was looking to the program right now.
Yes,
okay.
It's correct. Thank you so much again, both of you, and for the oral communicators. So see you at 2:30 this afternoon. Thank you. Thank you so much.
Bye-bye.
Bye.